document camera, and I'm not quite sure how this is going to work, but I'm going to try to give you something to set something on YouTube. All right, so there are two types of word problems that you do in calculus. One of them is called related rates, and we have completed those. The other type are these things called optimization problems. And there's good and bad news about the optimization problems. The bad news is these can get very ugly. If you take this course in college, the optimization problems that you do in college are going to be an absolute pain. The algebra behind some of it, some of the very typical ones, is just ugly. The good news is they don't ask that on the AP exam. They don't ask the ugly ones. So we're really not going to be doing a whole lot of the ugly ones. What we are going to do today, my main goal is kind of hit the highlights of what is an optimization problem, how do you do it. I'll probably get through three, maybe four examples, and then we'll pick up there tomorrow. And you do have a short assignment out of your textbook that's got 5 problems, and we'll pick up there tomorrow. So let's get started. First, what is an optimization problem? Well, an optimization problem, they have keywords like create something that's a maximum, something that's a minimum, what's the greatest, largest, something that it's looking for some sort of extreme. And what I'm going to do is we're going to start, I did send these out. These are in the notes, in your notes section. You have a Unit 5 section in OneNote. These are just problems out of a textbook that I use. And if you want to have the printed version of, or look up that, if you can somehow do a split screen. If not, I had to print them out, and then I had to print them out again to try to get the print larger to try to use this document camera. And hopefully, can y'all read that on your screen?
Yeah.
Oh, okay. As long as you can read it. So the first couple we do are going to be very basic. These are going to be the most basic optimization problems in existence. But when we do these basic ones, I'm going to highlight the ideas of how you solve all optimization problems. So here's how it works. So the first one, so we're going to do problems 2, 5, and 6. So when I look at problem 2, it says, find two numbers whose difference is 100 and whose product is a minimum. And when you ever do an optimization problem, first, because they're asking us to find a minimum, we know it's optimization. The first thing you look for is what you're trying to optimize. And they're pretty good about identifying it. They'll say, we're looking for the greatest, the smallest, the maximum, the minimum. And in this case, it says, I'm looking at this, it says whose product is a minimum. All right, so I'm looking for two numbers whose product is a minimum. So what I'm going to do is, write a function about the product. So if I've got two numbers and I'm interested in their product, I'm going to put P is equal to, and the two numbers I'm going to use are X times Y. Now, give you an idea of what we're going to do is when we find a maximum or minimum, we are effectively looking for a critical point. Like, think about when we were doing curve sketching, a maximum is here, a minimum is here. Your maximum is, at this critical point, your minimum's at this critical point. So what we're going to end up doing is finding a critical point. Take the derivative and set it equal to 0. And that's exactly what's going to happen here. We're going to take the derivative of this and set it equal to 0. We have a problem. Our problem is we have two variables. And you can have multiple variables when you do related rate problems, but when you're doing optimization problems, you need one variable here, and so that's our problem. Well, how do we fix that? Well, we look back at the original question. When we look at the original question, there's always some number we haven't used. In this case, this 100. And it gives us some information. It says two numbers whose difference is 100. Well, when I translate that equation, two numbers whose difference is 100, I'm going to say y minus x is equal to 100. I've just translated that equation. What we end up with is, I call it my helper equation. So pretty much every related rate problem you're going to do, you're going to get a function, and you're going to get a helper equation. The function is what you're going to take the derivative of. The helper equation helps us do that. And what that does is this helper equation helps us get this all one variable. So when I look at this equation, it says y minus x is equal to 100. I can rewrite this and say y is equal to 100 plus x. And now what I've done is everywhere I see a y, I can write 100 plus x. So I can take this, stick that into y, so end up with p is equal to x times 100 plus x. And I'll do a little work here. So I'll get p is equal to 100x plus x squared. Now, at this point, I am ready to take the derivative. Also, I want everybody to kind of realize we have done zero calculus. Right? So far, I've just done algebra stuff. I've translated, I've gotten a function, I've gotten my helper equation, I got everything into one variable. In this case, I picked x. And now my goal is, if I'm looking for things to be a minimum, right, which is what I want, I need to find my critical value. So I find my critical value, so I take the derivative, and that's going to give me 100 plus 2x, set that equal to 0, and 2x is equal to negative 100, x is equal to negative 50, and if I know that x is equal to negative 50, I can plug that back up here and find out that y is equal to 100 minus 50, and so y is equal to 50. And so I have now found two numbers, right, that hopefully have a minimum, I found my critical value. And so the two numbers I'm interested in are going to be negative 50 and 50. And if you think about it, if I multiply those two together, that's going to be a pretty big, that's going to be a pretty negative number compared to everything else. But we need to talk a little bit. Now, as far as questions that I've seen on the AP exam, on a multiple choice section, they may be like this. They're actually kind of like this, maybe a little harder. But on a free response, if you did this work and you came up with, okay, the two numbers are going to be negative 50 and 50, you would not get full credit because you really haven't established it's a minimum. So when you find your critical value, you take the derivative, set it equal to 0. All you've done is you said, well, I've got a flat spot. But as we've learned before, a flat spot could be a maximum or it could be a minimum. How do you tell? Well, there are a couple of ways, but I'm going to tell you, the way I want you to do it is we're going to look at the second derivative. And so when I look at the second derivative, let's see, take the second derivative of this, I just get 2. And let's see, so if the second derivative is equal to 2, I think we can agree that 2 is greater than 0. And since we have our second derivative is greater than 0, what we have now is our first derivative is 0, so we get a flat spot. Our second derivative is positive, so we have a happy face. If you try to draw a happy face on a flat spot, that's guaranteeing that you get a minimum. In fact, you don't have to explain because you get derivative of 0, and the formal explanation of this is a minimum. You can say the derivative equals 0 and the second derivative is positive. And that is sufficient explanation to certify that that's a minimum. So, recap the problem. Right? So in our most basic example of an optimization problem, the first thing you do is you hone it. The first thing you look for is what are you trying to optimize? Is there a maximum or a minimum, greatest, smallest? We're going to see some examples. And whatever you're trying to optimize, write that function down. That's what we're going to take the derivative of. Now you're typically going to have a problem because there's going to be multiple variables, and you can't take the derivative with multiple variables. So then you look back to the question, and hopefully there's usually another number you haven't used, in this case the 100, and it says the two numbers whose difference, so we write down an equation. That's my helper equation. I use my helper equation to make my original function all one variable. Then I can start the calculus where I find the critical value of, and sometimes the questions are sneaky. Sometimes they'll ask just for the x value. Sometimes they'll ask for the x and the y value, so you have to plug it back in. But you also have to establish that it's actually, in this case, a minimum. And the way we do that, look at the second derivative. And when you look at the second derivative, if it's positive, if you draw your, okay, yeah, if it's positive, then you can, then you know that that's enough to say it's a minimum. All right, so next up, let's look at problem 5. All right, so number 5, it says, find the dimension of a rectangle with a perimeter of 100 meters whose area is as large as possible. All right. Now we're getting into something, at most of these optimization problems, there's a picture involved. The first one, there was no way to have a picture. You're just talking about numbers. So, so it says find the dimensions of a rectangle, all right? Well, so if they talk about a rectangle, you draw a rectangle. And pictures are great, but if you don't label them, they're worthless. So I like using X and Y, and typically when I draw pictures, the horizontal links I call X and the vertical links I call Y, because it kind of models the, your coordinate plane. And so now I have a rectangle. It has perimeter 100 meters, and I want the area as large as possible. So what are we trying? All right, so now I'll do my little, try to do the teaching part, because otherwise it's really boring just hearing me talk. So what are we trying to optimize? You can chime in or type in or something. What are we trying to optimize? What thing are we trying to find, are we trying to optimize?
The dimension.
The area. Well, no, it says we're trying to optimize area, right? If you look at it, it says area is as large as possible, right? So our main focus is talking about area. So we're going to write a formula for area. Right? And I'm assuming everybody remembers, okay, area of a rectangle is x times y. This is what we're going to take the derivative of, right? I got area as, this is, we're going to take the derivative of this, set it equal to 0, establish, in this case it's a maximum, but we have a problem. Our problem is we have two variables. So I need a helper equation. And so when I look for my helper equation, I look back at the question, and I say, oh, I have this other number. All right, it says the perimeter is 100 meters. So I need a helper equation. What's my helper equation?
Two x plus 2y equals 100.
Perfect, right? Just perimeter, right? It says the perimeter is 100. Based on my picture, I have 2x plus 2y is equal to 100. And so now I have my helper equation. Now I can use this equation to make sure I get a bunch of x's, that I get all one variable. I like keeping things in terms of x's, so solve for y. And so I get 2y is equal to 100 minus 2x, and y is equal to 50 minus x. So now I have, here's my equation, and now what I'm going to do is, rewrite this so that I have all one variable. So everywhere I see a y, I'm going to plug this in. So I get a is equal to x times 50 minus x. And now, and I guess before I actually start doing calculus, I'll make my life a little bit easier and say a is equal to 50x minus x squared. And now I get to do the same thing I did in the previous problem. I want to, do the calculus part. I want to find out, I'm looking for a maximum. And so take the derivative of this. That's going to give me 50 minus 2x, set it equal to 0. When I solve, I find out that x is equal to 25. So that's my critical value. That's great, right? That means I have a flat spot. I want to establish that it's actually a maximum. So I'm going to take the second derivative, and when I take the second derivative of this, I get a negative 2. When I look at that, well, this is negative, right? So it's less than, so my second derivative is negative, which means I've got a flat spot and a sad face, which guarantees that I have a maximum. So I know that this is a maximum, or the largest. They're asking for dimensions, and so when I find dimensions, I need to figure out the y value. So I plug the 25 up here, and that's going to give me y is equal to, 50 minus 25 gives me 25. And what I end up finding now is, turns out that the dimensions that's going to have the greatest area is a square, which should make sense. Pretty much whenever you're dealing with symmetry of things, of any object, all the sides are going to be equal. So it turns out like the greatest area is going to happen when you have an equilateral triangle. Greatest area of anything is when all the sides are the same. So when I looked at, what I wanted to do, start off with optimization problems, I wanted to start off where the words weren't they weren't very wordy. Some of these problems do get kind of wordy. I also wanted to make sure that, the algebra on it wasn't terrible, right? Because you go through, both of these effectively are parabolas. And in years where I've taught Algebra 2 or Pre-Cal, I've actually included a problem like 2 and a problem like 5 on assessments when we talk about parabolas, because that's what we did, right? We looked at both of these. This is basically a parabola turning down, and you're looking for the vertex. In this other problem we did, this is a parabola turning up, we're looking for the vertex. But it's not always going to be a parabola, which means we need to look at problem 6. Okay. So problem 6 says, find the dimensions of a rectangle with area 1,000 square meters whose perimeter is as small as possible. All right? So in this case, what are we trying to optimize? Not everybody at once. Perimeter, right? Okay. We're trying, because it says, oh, whoops, I forgot to. First rule of calculus, draw a picture. We have a rectangle. There's x, there's y. So I'm optimizing the perimeter. Now let's see. Guess the same thing we had last time. Our perimeter is going to be 2x plus 2y. And this is what we're going to take the derivative of, right? We're going to take the derivative of this, find our critical values, right? Check to make sure in this case it's a minimum. But we have a problem, right? Our issue is we've got two variables. So we need a helper equation. How do we get our helper equation? We look back at the original problem and look for a number we haven't used. In this case, they tell us we have an area of 1,000. So if I look at my picture, I'll say x times y is equal to 1,000. There's my helper equation. Okay? I'm going to do the same thing. I'm going to get one of the letters by itself, so it's going to give me y is equal to 1,000 over x. And plug this in for y. So it's going to give us p is equal to 2x plus 2,000 over x. And honestly, of the examples, the first two examples, you don't need to write those down. I kind of want you to write this down because this is a little more representative of things that you'll have to do. So if you haven't done so, I don't care about you writing the problem. You can find that in OneNote. But I do care about you drawing the picture. Write this equation, draw the picture, and write your helper equation. And then you get here. There's something a little more complicated about this one than the previous two. Namely, it's not a parabola. All right. So now, do the same thing I did before. I've got to take the derivative. So this is going to give me, I'm probably going to rewrite this and say this is 2,000 times x to the negative 1. So when I take the derivative, this gives me 2 minus 2,000 x to the negative 2. Take my derivative. I'm going to set that equal to 0. And now solve, so that's 2 minus 2,000 over x squared is equal to 0. 2 is equal to 2,000 over x squared. And I got x squared is equal to 1,000. And this gives me x is equal to, the square root of that is 10 square root of 10. Now, normally, like if you're just solving regular equations, when you get square root of both sides, you need plus or minus. But we're dealing with real life situations, and you don't get a negative length, so we ignore we don't worry about the negative part. But the reason I wanted you to write some things down is, I don't know if this is actually a max or a min. All I know is this is a spot this is where I have a flat spot. So what I need to establish that this is, we are looking for a minimum. I need to establish that I'm going to get a minimum. What do I do? Well, we're going to look at the second derivative. And when I look at the second derivative, well, that goes away, and that's going to give me 4,000 x to the negative 3, which I'm going to write down as 4,000 over x cubed. All right. So now what happens? Well, like the previous problems, when I took the second derivative, I either had like a positive 2 or a negative 2, and it was very easy, well, if to determine if it was positive or negative. What do you do in this case? Well, technically, this is not just p prime, it's p prime of x, and this is p double prime of x. And so I need to know, well, what's p double prime of this particular x value, which in this case is 10 square roots of 10. So that means I actually have to plug the x value into this. And so that's 4,000 over 10 square roots of 10 to the third power. Now, do I need to, I guess technically I guess I could compute this, but I really don't care what the number is. All I know is, well, 10 square root of 10 cubed, this whole thing is going to be a positive number, so I can guarantee that this is positive. And so now what I know is at 10 square roots of 10, I have a flat spot, and I also know the second derivative is positive, so I have a happy face, which means, I've got this picture. So that's enough to say it's a minimum. But if I look back at the original question, I think they didn't want to know what's one side of it. They want to know the dimensions. So that means I need to figure out what a y is. So when I plug back up here, I get 1,000 over 10 square root of 10. And actually, after you simplify it, you end up with 10 square roots of 10. And major surprise, with the perimeter as small as possible, that's going to be when you have a square. It's the same thing you get. These two problems they're almost asking the same question. And like this one says, if you've got a perimeter, what gives you the biggest area? Well, it's when you have a square. All right. If you've got a rectangle with a certain with a certain area, what gives you the smallest perimeter? Well, it happens when you have a square. Now, here's a bit of warning. And we're not gonna hit the tricky one today. That's fun and excitement for tomorrow. The warning is the easy problems for optimization, your answer is going to be at the critical value. Right? If you look at these first three problems, all of our answers were at the critical value. Right? It's where our derivative equals 0 because it's behaving like it's supposed to. When we get to the trickier problems, your maximum or minimum may not happen at the critical value, and that's the sneaky part that the AP exam does. So we're going to try to do some of those in the next day or so. The really tricky optimization problems happen next semester, but I'm just kind of setting the stage that your answer isn't always going to, there's going to be some problems where you do all this work, you take the derivative, set it equal to 0, do all this lovely calculus stuff, and your answer isn't that. Like you do all this work, and this case, I needed it to be a minimum, and so my critical point was at a minimum, and yay, I got the answer. But what happens if your critical point's at a maximum? How do you find the minimum? Those are some questions we're going to talk about when the questions get harder, but not today. All right. Is this making? I want to pause this, and I don't even know what the